This is Chapter 1 lecture, Part 1. And so the first part of Chapter 1 talks about touchscreens and how they work. Well, touchscreens, they work by responding only to certain stimuli. And the certain stimuli that touchscreens respond to are those stimuli that conduct electricity and have surface area that's similar to your fingertip. So you are an electrically conductive body. And that's why when you touch the touch screen, it responds. Now, if you touch something with your touch screen that's not electrically conductive, like something made of plastic or something made of glass, then your touch screen will not respond. But if you touch it with a metal, and if that metal is similar in surface area to your fingertip, then your touch screen will respond to it. And so in the first section of Chapter 1, you learned about the differences shown here in this table between solids, liquids, and gases based on shape, volume, and the proximity that the particles are to each other. Gases, those particles that make up a gas, are very far away from each other. They have complete freedom of movement, and therefore they have high kinetic energy. Also, gases have neither their own shape nor their own volume, but gases have the ability to expand to fill the shape and container that they're in, and the volume of the container that they're in. So gases expand to fill the shape and volume of the container. Solids have their own shape and volume. The particles of a solid are in very, very close proximity to each other. They are touching each other and therefore have no freedom of movement and therefore no kinetic energy. Liquids, on the other hand, the particles are close to one another, but they are not touching, and they have limited freedom of movement because they're so close to each other. And liquid particles have very, very low kinetic energy. Liquids do have their own volume, but they do not have their own shape. They take on the shape of their container. And we all know that we could convert between solid, liquid, and gas states. You can go from a solid to a liquid to a gas by adding heat. You can go in the opposite direction from a gas to a liquid to a solid by removing heat. Matter is classified as either a pure substance or a mixture. A pure substance can either be an element or a compound. Elements are substances that are composed of the same type of atom. Compounds, however, are composed of two or more different types of atoms. Mixtures, they contain more than one type of pure element. The different combinations that can be in a mixture are two or more types of elements, two or more types of compounds, or a mixture of elements and compounds can also make up a mixture. Pure substances cannot be broken down into any simpler means by physical methods. Compounds have to undergo chemical processes in order to separate the atoms from each other. Mixtures, on the other hand, can be the components of a mixture can be separated from each other by using physical methods like filtering or boiling or some other physical process. So for these questions, question 1, block A represents a compound because each of these two different circles, one dark brown, one light brown, represent a different element. So a compound is a combination of two or more different types of elements. So panel A is a compound. Panel B represents elements. And there are two different elements here. You've got the dark brown circle by itself. Unlike panel A, you have a dark brown connected to a light brown. So those two are connected to each other or touching. So therefore, you know it's a compound. But if each circle is separated from each other, it represents an element. And so you've got two different types of elements, the dark brown and the light brown. So therefore, this represents a mixture of two different types of elements. Panel C is also a mixture, but you see two different types of elements, just like in panel B, but then there's also a compound. So C is a mixture of two different types of elements and a compound. D, however, just represents an element because you got these brown, dark brown spheres representing the same type of element or the same type of atom. So therefore, panel D represents an element. And so here, question 2, we've got a list of different substances that we can classify as an element, compound, or mixture. Aluminum foil is made up of only aluminum atoms, so it's an element. Baking soda is a compound. It's a compound whose chemical or scientific name is sodium bicarbonate, which has the formula NaHCO3. So it's composed of four different types of elements. Na is sodium, H is hydrogen, C is carbon, and of course O is oxygen. So it's composed of 4 different types of atoms. So therefore it is a compound. Milk is a mixture. When we buy it in the store, it's a homogeneous mixture because it's uniform throughout. But when it comes out of the cow, it is a heterogeneous mixture. They put it through a homogenizer to make it smooth and uniform throughout. It's not lumpy. But when it comes out of the cow and settles, you have the heavier components of the milk. They sink and settle to the bottom. And so the homogenizing makes the milk uniform throughout and therefore makes it a homogeneous mixture. And homogeneous mixtures are also called solutions. Air is a mixture of oxygen, nitrogen, and water vapor mostly, as well as argon. Copper wire is an element because it's just copper. And sugar could be many different types of sugar like glucose or sucrose, but they're all compounds. The next set of questions, the first question asks for a calculation of the atomic percentages for each of the following compounds. So the first compound is BeCl2. If we go here to our periodic table, Be is beryllium. And when we look at the periodic table here, the number above the symbol for beryllium, Be, that number 4, that is the atomic number. The atomic number tells you the number of protons that are in the nucleus of that atom. The number underneath the symbol for beryllium is the atomic mass. The atomic mass tells you the number of grams per mole for that element. So beryllium has an atomic mass of 9.012 grams per mole. Another unit for atomic mass is the AMU, which stands for atomic mass unit. So beryllium has an atomic mass of 9.012 grams per mole. The other element that's a part of this compound BeCl2 is chlorine, Cl. And there are 2 chlorine atoms in the formula of this compound. Notice there's no little subscript number after the beryllium. So therefore, it's understood that there's just 1 beryllium atom in the formula for BeCl2. Even though that 1 is not there, by it not being there, it's understood that there is just 1. And so chlorine is right here. So the atomic number for chlorine is 17. So there are 17 protons in the nucleus of a chlorine atom. And chlorine's atomic mass is 35.45 grams per mole. So therefore, to calculate the atomic percentages for beryllium and chlorine in this compound, we need to first determine what's called the molar mass for BeCl2. The molar mass for any compound is just the sum of the atomic masses that we find on the periodic table. So beryllium, there's just 1 of them in the formula. And the atomic mass is 9.012. For chlorine, there's actually 2 of them in the formula for this compound. And each chlorine has an atomic mass of 35.45. And that gives you 70.90 grams per mole. You add that together. You get 79.91 grams per mole. So therefore, to find the atomic percentage for beryllium in this compound, you take the atomic mass for the beryllium for this compound, 9.012, divided by the total molar mass for the compound, 79.91, multiply by 100. The grams per mole units cancel. And that gives you 11.28% beryllium. So BeCl2 is 11.28% beryllium. The percent chlorine in this compound, we take the total atomic mass for chlorine in this compound, which is 70.90 grams per mole, divided by the total atomic mass, the total molar mass for this compound, 79.91 grams per mole, and then multiply by 100. And that gives you 88.72% chlorine. Now, we really didn't have to do this last calculation for chlorine. All we had to do was subtract 11.28 from 100, and that would have gave us the percent chlorine. Because there's only two types of elements in this formula. Once we find the percentage composition of one element, all we have to do is take that value, subtract from 100, and get the percent composition of that second element. Now, the next compound, TiOH4, has 3 different types of atoms instead of 2 different types. It has titanium, Ti, oxygen, O, and hydrogen, H. So we've got to find the percent composition of 2 of them, and then we can subtract that total percentage by 100, and then get the percentage of the third one. Or we could just do the calculation for that third one. Either way. But you've got to get the percentages for the first 2 correct to make sure that that third one is correct. So let's take a look at our periodic table. Find titanium, oxygen, and hydrogen on the periodic table. Titanium is here. It's atomic number 22. So that means there are 22 protons in the nucleus of a titanium atom. Its atomic mass is 47.88. Oxygen, atomic number 8. 8 protons in the nucleus of an oxygen atom with an atomic mass of 16 grams per mole. And then finally, a good old friend, hydrogen. Over here, it has an atomic mass of 1.008 grams per mole. And its atomic number is 1. It means it only has 1 proton in the nucleus of its atom. So now we'll do the same methodology that we did for the beryllium chloride compound. We take each element, note how many of those elements are in the formula of the compound, and then multiply that number of elements that are in the formula by the atomic mass that we get from the periodic table. So for titanium, there's only one of them in the formula. Again, there's no subscript, so it's understood to be 1. Notice that OH is in parentheses. And after the parentheses is a number 4. That number 4 is not just for the hydrogen, but it's also for the oxygen. So there are 4 oxygens and 4 hydrogens in the formula for this compound, which is called titanium hydroxide. The first compound is beryllium chloride. And then you got titanium hydroxide. Both of these compounds are ionic compounds, and we'll learn how to name ionic compounds in a later chapter, either chapter 3 or 4. In chapter 2, we learn how to name molecular compounds, and we'll get to that in the chapter 2 lecture. So there's only 1 titanium in the formula. And titanium has an atomic mass of 47.88 grams per mole. We've got 4 oxygens. Each oxygen is 16 grams per mole. So that's 64 grams per mole. And there are 4 hydrogens in the formula. Each hydrogen is 1.01 grams per mole. And that gives you a total of 4.08 grams per mole. Now we need to add these three numbers together to get the total molar mass of the compound. That gives you a total molar mass of 115.96 grams per mole. So now we're ready to calculate the percentage of each element in the compound. The titanium percentage is 47.88 divided by 115.96 times 100. The percentage oxygen is 64 grams per mole divided by 115.96 grams per mole times 100. And then the percent hydrogen is going to be 4.08 grams per mole divided by 115.96 grams per mole times 100. And so do the math. 47.88 divided by 115.96 gives you 41.3%. The percent oxygen is 64 divided by 115.96. And that gives you 55.2%. And then percent hydrogen is 4.08 divided by 115.96. And that gives you 3.5%. And so the next mathematical topic in chapter 1 is unit conversions, also called dimensional analysis. And so nanotechnology is a branch of chemistry, engineering, science, all rolled into one. And it is based on the manipulation of matter that has at least one dimension that is between 1 and 100 nanometers. 1 nanometer is equivalent to 1 times 10 to the negative 9 meters. So that is an equality expression because there's an equal sign there, but it's also a conversion factor. So it's an equality, but it's also a conversion factor. A conversion factor, therefore, can be written as an equality, as we see here, but it can also be written as a fraction. If 1 nanometer is equivalent to 1 times 10 to the negative 9 meters, then for every 1 nanometer, there is 1 times 10 to the negative 9 meters. So 1 nanometer per every 1 times 10 to the negative 9 meter. We can also write the conversion factor that is the reciprocal of this one. And therefore, we can say 1 times 10 to the negative 9 meters per every 1 nanometer. Both mean the same thing. So if we have 32 nanometers, that is equivalent to 3.2 times 10 to the negative 8th meters. To do the conversion, we take 32 nanometers, and we want to multiply that 32 nanometers by the conversion factor needed to convert the nanometers to meters. Well, we want to get rid of nanometers, and we want to convert those nanometers to meters. So we would want to use this version of the conversion factor, because our conversion factor is also a fraction. So in our fraction, we want the unit that we want to get rid of to be in the denominator. The unit that we want to convert to needs to be in the numerator. The numerator is the top part of the fraction. The denominator is the bottom part of the fraction. And now that I've got my units where they need to be, which unit needs to be in the bottom? Nanometers, because I'm getting rid of the nanometers. I'm converting from the nanometers. The unit that I want to put in the numerator is the one that I'm converting to, the unit that I want, which is meters. And now I put the numerical values that go with those units that are in my conversion factor. So 1 times 10 to the negative 9 meters per every 1 nanometer. The nanometers cancel. And I do my math. 32 times 1 times 10 to the negative 9 is 32 times 10 to the negative 9 meters, which is also equivalent to 3.2 times 10 to the negative 8 meters. So that's how you convert from one unit to the next. You've got to know what the conversion factor is, and then set up the problem, write down the value that you're given, and then multiply that value by the conversion factor that's needed to convert between those units. The unit that you're getting rid of, it cancels. You do the math, you get your answer. So taking a look at another set of questions. Review of scientific notation. If you have a number that's greater than 1, then you'll convert it to scientific notation by putting a decimal at the end of the number if there's not a decimal already in the number. And then you'll move that decimal until you have it between the first 2 digits, the first 2 non-zero digits in the number. And then you count how many spaces it was required for you to move that decimal. So I moved the decimal 1, 2, 3 spaces. So my answer in scientific notation for this number is 1.5. And then to express my exponential, and because I moved that decimal 3 spaces, then I write times 10. That's my exponential. And the superscript, which is my power, represents the number of times I moved a decimal. And I moved it 3 times. So my answer is 1.5 times 10 to the third. Now, when you have a very small number, like in part B, a number that's less than 1, you're already going to have a decimal in the number. So you just move the decimal until it's between the first 2 non-zero numbers. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I moved it 11 spaces. So that's 9.58. Then I write my exponential expression times 10. I moved it 11 spaces, so I do my superscript for my exponent, 11. But this is a very small number. It's less than 1. Whenever you change a very small number that's less than 1 to scientific notation, you put a negative sign in front of your exponent. So 9.58 times 10 to the negative 11. Part C, we've got another small number. We need to move the decimal 1, 2, 3, 4, 5, 6 spaces. So the diameter of a red blood cell is 7.5 times 10 to the negative 6 meters. And it's negative 6 because that is a very small number. That's less than 1. Question 2, we need to convert 1 meter to centimeters, micrometers, nanometers. Here's your prefix table for metric conversions, giving you basically the multiplication factor, which is your conversion factor. This is your centimeter to meter equality, which, as we showed in the previous example, that we can take that equality and convert it to a fraction, which is also a conversion factor that means the same thing as the equality. So there are 1 times 10 to the negative 2 meters per every 1 centimeter. And we can also write the reciprocal. For micrometers, so we have to do convert a meter to centimeter, convert a meter to micrometer, and convert a meter to nanometers. The micrometer is 1 times 10 to the negative 6 meters per every 1 micrometer. One times 10 to the negative 6 meters per every 1 micrometer. And of course, we can write the reciprocal of that. That means the exact same thing. And then the nanometer to meter conversion. Here's the equality. There's 1 times 10 to the negative 9 meters for every 1 nanometer. So those are our 3 sets of conversion factors for question number 2. So 1 meter is equal to 1 times 10 to the negative 2 centimeters. And so to get that answer, 1 meter, I want to convert meters to centimeters. I want to get rid of meters, so meters need to be in the denominator. I want centimeters, so centimeters need to be in the numerator. So we take 1 times 1, that's 1. And then we divide by 1 times 10 to the negative 2, and we get 1 times 10 to the positive 2 centimeters. For the meter to micrometer conversion, Again, we want to get rid of meters. So meters go in the denominator. We want micrometers. So that goes in the numerator. We look at our equality, our conversion factor for meter to micrometer conversions. And there is 1 micrometer for every 1 times 10 to the negative 6 meter. The meters cancel. We multiply 1 times 1, that's 1, and divide 1 by 1 times 10 to the negative 6. We get 1 times 10 to the positive 6 micrometers. And then finally, converting 1 meter to nanometers. We want to get rid of meters, so it goes in the denominator. We want nanometers, so nanometers go into the numerator. We get our numbers that go along with those units for our conversion factor. For every 1 nanometer, there's 1 times 10 to the negative 9 meters. We do the math, we get 1 times 10 to the 9th nanometers. Question 3, how many nanometers is 545 centimeters? This is a 2-step conversion. We first need to take the centimeters and convert to meters. Then we need to take the meters and convert to nanometers. We know our centimeter to meter conversion factor. And we know our meter to nanometer conversion factor. So first, let's take the 545 centimeters and convert to meters. We want meters. We want to get rid of centimeters. Centimeters therefore go in the denominator. Meters go in the numerator. And for every 1 meter, for every 1 centimeter, there's 1 times 10 to the negative 2 meters. Centimeters cancel. Now we've got meters, but we don't want meters, we want nanometers. So now we need to convert the meters to nanometers. We want to get rid of meters, so meters go in the denominator, nanometers go in the numerator. For every 1 times 10 to the negative 9 nanometers, there is 1 meter. I got that wrong. For every 1 nanometer, there is 1 times 10 to the negative 9 meters. So the meters cancel. Now we need to do the math. 545 times 1 times 10 to the negative 2. And then we multiply by 1. We get that same number. And then we divide by 1 times 10 to the negative 9. And we get 5.45 times 10 to the 9th nanometers. The next question, how many millimeters is 0.0387 nanometers? This is another 2-step conversion. We take the nanometers and first convert them to meters. And then we'll convert the meters to millimeters. Here's our millimeter conversion equality. For every 1 times 10 to the negative 3 meters, you have 1 millimeter. So there's our conversion factor for converting between meters and millimeters. So let's first convert the 0.0387 nanometers to meters. Nanometers go in the denominator, meters go in the numerator. The nanometers cancel. Now we'll convert the meters to millimeters. The meters go in the denominator. The millimeters go in the numerator. The meters cancel. So now we do the math. 0.0387 times 1 times 10 to the negative 9 times 1. We get 3.87 times 10 to the negative 11. We need to divide that by 1 times 10 to the negative 3. And we get 3.87 times 10 to the negative 8 millimeters. Question 5, the majority of new smartphones being released have displays that are at least 5 inches in size. What is this size in centimeters? There are 2.54 centimeters in 1 inch. This is a conversion factor. And inches are abbreviated IN. So we take our 5 inches and we need to convert the 5 inches to centimeters. So inches go in the denominator, centimeters go in the numerator. There's 1 inch for every 2.54 centimeters. The inches cancel. So 5 times 2.54 is 12.7 centimeters. So the next topic is on subatomic particles, and there are 3 of them: protons, neutrons, and electrons. Protons and neutrons, shown here for the helium atom, and the hydrogen atom doesn't have any neutrons. The hydrogen atom only has 1 proton and 1 electron for the hydrogen atom. The proton is shown here in the nucleus. The nucleus is the brown sphere, and the little blue circle inside is the 1 proton that hydrogen possesses. And hydrogen, just like all neutral atoms, they'll have the same number of protons as electrons. So by hydrogen having 1 proton, it also has 1 electron, shown there in the light blue sphere. Helium has an atomic number that's 2. So helium's atomic number is 2, whereas oxygen's atomic number is 1. So hydrogen has 1 proton and 1 electron. Helium has 2 protons and 2 electrons. So there are your 2 protons, and there are the 2 electrons. And helium also has 2 neutrons, shown there in the green spheres. And so the mass number of an atom is the number of protons plus the neutrons. So helium has a mass number of 4 because it has 2 protons plus 2 neutrons. The number of neutrons can always be calculated by taking the mass number and subtracting from it the number of protons. So to complete this table, aluminum is atomic number 13. That means aluminum has 13 protons and 13 electrons. It has also 14 neutrons. This isotope of aluminum in this table is shown to have 14 neutrons. So the mass number is going to be the number of protons plus the number of neutrons. 13 plus 14 gives you 27. The next row, well, we don't know the identity of the element, but we do know how many protons it has. So the number of protons does tell us the identity of the element. The number of protons is the atomic number, and that gives the element its identity. Each element has its own unique atomic number. No 2 elements have the same atomic number. The element that's atomic number 2 is helium. And helium's mass number is 4. Helium, just like all atoms that are neutral, have the same number of protons and electrons. And the mass number minus the number of protons, 4 minus 2, gives us the number of neutrons, 2. The next row, we have 19. The element in question has 19 protons. So we find the element that's atomic number 19. And that is potassium, K. If there are 19 protons, then there are also 19 electrons. And then to get the number of neutrons, we take the mass number, 39, and subtract from it the number of protons, 19, and we get 20 neutrons. And next we have the element chlorine with 18 neutrons. You look on the periodic table for chlorine, it's atomic number 17. So therefore there are 17 protons and 17 electrons. And we're also given that there are 18 neutrons. If we add the protons plus the neutrons, 18 plus 17, we get 35. And then last on the table, we have 26 protons. Atomic number 26 is iron, symbol Fe. If we have 26 protons, then we have 26 electrons. If the mass number is 56, 56 minus the number of protons, 26, gives you 30 neutrons. And so notice the periodic table is arranged in rows. These rows are also called periods. And then they're also arranged in columns. And you see the columns have numbers. So these columns are also called groups. And elements that are in the same column or group have the same or very similar properties. And so that brings me to the end of part 1 of the chapter 1 lecture. I'll be recording part 2 of the chapter 1 lecture and posting it to our eLearn site news section as well. So please look at the news section and you will find this recording.